So in chapter 6, we're going to be looking at orthographic projection, and this is going to be the basis and the fundamentals of how we lay out a drawing in order to create it so that somebody can make it. Okay. Now, orthographic projection is going to be based on a way that we visualize it, and it's according to our ANSI standard. So laying parts out in orthographic projection is part of the dimensioning standard. Okay. So here we're gonna be looking at recognizing and sketching the symbol for third angle projection, which is the angle of projection that we use here in the United States. Everybody else besides United States and Canada use first angle projection. So we'll talk about the differences between those, but for the most part, here in the United States and in our program, we're going to be practicing the third angle projection. We're going to be finding out that there are 6 principal views, and we're going to be choosing on any given drawing. We're not going to always draw 6 views. We're going to pick the 2 to 3 that are most important. Okay. If we do need extra views beyond that, then we can add them. But for the most part, most often it's going to be 2 or 3 views that is going to get us what we need. We're going to be looking at the application of the top, front, right side views of an object and see how when you're normal, inclined, or you have oblique surfaces to those and how that changes how they look. We're going to understand which views show depth, height, and width. And then we're going to practice those on the assignment that I have for you. Let's see here. I don't know. There's some other things that we're going to do, but I'm not going to just read these to you. Let's jump in. Okay. So first of all, understanding projections. We introduced this idea in chapter 13 a little bit when we started sketching, if you would, the front profile of a part. So we practiced that. I don't know, we had 4 or 5 different sketches that we looked at, and we basically identified a way that we're going to be looking at it. And now we're going to draw what we see when we're right in front of it, for instance, looking straight on. So in this case, we're going to look at this part. I don't know what it's called. It's not telling us, but you've got this half circle going up on top. We have the base or the feet that are coming out in front. And we see this, what I would call an isometric view of it, okay, or a pictorial view of it. In here, you're going to notice that they identify the dimension that is going to show how tall it is as the height, the dimension that shows how wide it is as the width, and then the dimension that shows, how far back it goes as the depth. Okay, so they're kind of identifying he's here on this view. Now, over on the right-hand side, if we identify that if we take where we call this a line of sight, and we are going to look in this direction, okay, this way, the view that we see over here on the right is called the front view, okay? Now, the front view is going to be the first view that we project everything else off of. And the front view is going to be important because it's going to do 2 things. It's going to give us the main shape of the part, okay, kind of like the overall. It gives us the best view of what that part looks like, or that item. And it's also going to have one of the longest dimensions in the part. So in this case, we can see that the height is the tallest or the longest dimension. The front view is going to contain the height then, okay? If the length was the longest dimension, the front view would contain the length, okay? So it will be a longer part. It's going to give us the best representation of what that part looks like, and it's going to also contain the longest dimension, okay? You'll also notice here that when we look straight on, we see 2 of these items between width, height, and depth. We see the width right here, how wide it is, and we see how tall it is. But we do not see a dimension, or we don't get from this view how deep it is, right? We don't see that. We would need another view to do that. Okay, we would need another view. And we could get that from one of 2 views. You could look at it from the right side. Do you see that in this direction? We would look at it at the right side. And then we would draw, if you would, kind of a backwards L. Okay. Or we could look straight down on it and we would see what the depth was as well. Okay. So we have options. We could either do both, or we could do one, which one makes sense. It's kind of, up to the designer to determine that based on what he or she would feel that down the line, the next person would need to make that part. Okay. So this is kind of like our first front view. As I said, there are 6 principal views of any part. the first one, the main one, is going to be that front view. And like I said, that is the most important one. It's the one that we pick first, and we pick it based on the major shape of the part and that it has the longest dimension in it. Okay. Will that happen each and every time? I can't say 100%, but probably 97% of the time it's going to be that way. Okay. All right. So when we look at it, this would be the front view. They identified that. Then if we look straight down, that's going to be our top view. Our right side view is going to be on the right-hand side of the front view. Our left view is going to be on the left-hand side of the front view. The bottom, it's going to come up from the bottom opposite the top. And then the rear is going to be the opposite side to the front. Okay. Now, multi-view projection, and this is kind of that classic example of looking at a house, okay, and thinking about, okay, if I stand right in front of a house and I just draw what I see, that's going to be the front projection, okay? If I go to the right side, 90 degrees to that, and I look at the side of my house, and it's from that right side, from the front view, that's going to be the right side view or projection, or in this case, they call it elevation, as we know, and so on, okay? So we would line up by the front view, the right side view. Notice that the top of the chimney is in line all the way across the right side view, the front view, the left view, and that rear view, okay? And then if we look at the left side of the house, or I'm sorry, the right side of the house, and we're gonna put in line all of these items, kind of drives me nuts because this front view is just shifted to the right a little bit, but these should be all in line from top to bottom, okay? So orthographic projection means that we have everything all in line across each one of the views. We might see something different in a view, but in the case of, I like the chimney as my best example here, the chimney is straight across in all 4 of those views, okay? 6 standard views, as we've mentioned: front, right, left, top, bottom, rear, okay? Now, when we look at this part, they kind of show this nice little progression, if you would. So we start up here. This is the front view. They're showing it straight on, and I would draw what that front view would be. Then what I'm going to do is I'm going to turn it 90 degrees. So we're turning, and then right here, once I get to that 90 degrees, turning it to what would be the right side view. Then I would draw what that looks like literally on the side. If I wanted to look at the top, I would start at the front there again, and I would tip it towards myself until I saw, tip, the exact top side of that view. Make sense? So again, kind of a way to visualize. A lot of times you're not going to have, or most often you're not going to have a part in front of you. You're going to have to kind of figure out what that's going to look like. Okay. And that is something, it's not a skill that you automatically get, but all of a sudden it'll start making a little sense. So in the beginning here, depending on your experiences, it might come easy to some people. Maybe they've worked in a machine shop and looked at prints quite a bit. And all of a sudden you're like, oh yeah, I've done that before. I recognize it. It's not a requirement of this class. So you might not have those experiences. That's okay. So we're going to continue to practice and work on these things. And all of a sudden it's going to click. Okay. It will. I promise. It always does. It always does. By the exercises and the things that we do. Now, principal views are always going to contain 2 of the following: height, width, and depth, okay? Depending on the view that you're in, you're not going to see all 3 of them ever, but you're going to get 2 of those in each one of our views. And we saw how width and height were found in our front view earlier. Projections, we already talked about this. A projection is really projecting to a surface, and that surface really is our piece of paper that we're going to draw on. And we're drawing what we would see when we look at that view. So if it's a front view straight onto the part, we're gonna basically project all of the points, if you would, forward to your paper so that we can draw what that view is going to look like. Do you kind of see that? Okay. So again, it's like taking that part and showing it. What do I see when I'm standing right in front of it? On the right side of it, top of it, bottom, whatever it might be. Horizontal and profile projections. So horizontal and profile projections just mean that this is the line of sight perpendicular to that horizontal plane where I would show the top view, okay? The right side view is going to come from a profile projection, and that's just going to be the side profile that we're going to see through that lens, if you would, that line of sight. Now, a very helpful visual is a glass box. Okay, a glass box. If I have a glass box and it has, you know, a standard 6 sides and each one of those are mutually perpendicular to each other, okay? You'll notice that if I am able to suspend my part inside of that glass box, and I take that glass box and I look straight on in any one of those sides of the box, I could project forward what each one of those sides would look like, right? Okay. Now, if I take that box and I start to unfold it with my front view being the one that everything hinges off of. So notice that I'm going to hinge this side of my glass box up, which is going to be my top view. If it was down and in the box form, like we see up here, it would be the top view looking straight down. But now I want to create a drawing and I'm going to take that, I'm going to hinge that up. Okay. I'm going to hinge out my right side view, my left side view, and then my rear is going to come back. And you're going to notice that I end up with an unfolded box like we see here. Do you see that? How we kind of progressed from 2 slides ago to here? Okay. This is orthographic projection, standard orientation of standard multi-views of a part. The front view is in the middle. The top is on top. The right side is on the right side. These 3 are like the most popular principal views, okay? Right or left side, depending on what's going on. Now, you'll notice a couple things here. Orthographic projection. Everything has to be in line across the views. So we're never going to pick 6 views. We're going to pick the 3 best, the 2 or 3 best, okay? That is going to get our information across. But if I pick the front and the top, notice how this left side is in line across the views. Notice how if I go straight up for where the center of this hole is, and we show, notice here's the center line for what would be the hole in this view, right? It's hidden in this view, but we know that it's there. So it's depicting it so we see the sides of that hole instead of it as a circle, but that center line is in line, okay? The right edge of that part in line, okay? Orthographic, it has to be that way. You can't have it shifted left or right. When we create multi-view drawings, they have to be in line across the views, all of them. And that's what makes it easier to understand what different elements are too, okay? As we go right to left, height-wise, we have the very top of our part here in the front view. If I go over to the right side, notice that that's the very top of the backwards L, if you would, in the right side view, okay? The bottom of the part, in line across that right side, okay? If I go to the left side, same thing. And then remember, this is an extra hinge. This is the back side brought forward, okay, on my box. So then these are all in line across the top, the bottom, and the centers of those holes, too, every one of those elements, okay? All right, this is good. As we look here, you're going to notice now this goes back to when we would construct our views using manual means like compasses and things like that, where we would have folding lines. These folding lines would represent the hinges on our box, okay? And you'll notice that however deep this view in the top is how deep from the folding line the right side or the left side is going to be. And that's what they show going down here like this, okay? When we start laying out orthographically projected multi-views, I'll be kind of teaching you this as you go along, okay? As you go along. For right now, we're going to be sketching it in the first part here, but then we're going to be, when we start doing it in CAD, we'll start identifying some of these distances so that we can see how those are developed. So, all right. Transferring depths. There's a number of different ways you can transfer depths, but probably the most efficient and the easiest is using what we call a miter line. Okay, so that's a 45-degree angle so that when I'm developing my right side view, I can get its depth and I can go over that 45-degree angle and I can find how deep it's going to be over in this view. And then I'm going to line up the bottoms and the top from the front view. So again, those are techniques that we're going to practice when we start laying out multi-view drawings. It won't be this week in AutoCAD, but I think it's going to be next week actually, okay? So that'll start coming. Now, necessary views, okay? This is the rule with necessary views. I have to see all of my features in at least 2 views, Okay. And sometimes I can accomplish that literally with two views. Okay. If it's a simple part that, let's say, is a very simple turned part, I only need a front and maybe a side view to show the profile. I can be done. Okay. If I had a drawing of my pencil, okay, my pencil, I'm going to go underneath my thing here. Okay. Zoom out a little bit. So if I have my pencil here, okay, there's not much to my pencil. And imagine, I know there's flats on it, but imagine it's just a round pencil, okay? All I would really need to know is how long it is in this view, right? For the most part. And then if I would draw it from the side view, what is the diameter? I could get away with two views for a very simple part like a pencil, okay? But if I have more elements, more features, I have to be able to identify in two views each one of those features. So that's where I start getting into more views. And the more complex the part is, usually the more views that we need to actually show everything. So 2 at least. 3 is usually a pretty darn good number, but then sometimes we get 4 and 5 because we just need to grab some more extra information. So you'll notice here that on this part, they picked the best 3 views. You're always going to have a front. Remember, major shape of the part is the front and the longest, or in this case, the tallest dimension. And then in this case, they picked 2 other views. Okay. They picked the top view and they picked the right side view. Now, as we look here, the other thing that you want to do is when you pick your 3 views, why wouldn't you pick one or the other? Well, sometimes it might not really make a difference. So whether you pick a left side view or a right side view might be how you have more room on a drawing. It might be, okay, as long as there's no difference between them. In this case, if I look at my right side view, my left side view is exactly the same, except it's flipped, right? But if I look top view to what would be the bottom view, why would I pick the top view? Another rule is you want to pick the views that have the fewest hidden lines. Now you're getting like actual visible edges. So on the bottom view here, you're going to notice that we have a hidden line going across horizontally because we would be looking up through the bottom of the part and we wouldn't see that edge. But when we're looking down, I see that as an edge. There's one less hidden line in the top view. That would qualify the top view as being the better one to choose. Does that make sense to everybody? Okay. Just some things to think about as you're picking views. Because you might be like, okay, which one do I pick? Front is always major shape of the part and one of the tallest dimensions or the longest dimensions. Okay. And then the rest of the views are going to be projected from it. You could not project a rear view from the front view without having the left side view in the middle. Okay. You can't project 2 views over. You have to project when you open up your box, if you would, whatever that hinge was. Okay. So that's kind of one of the rules. Choice of views to fit paper. I don't necessarily agree with the word poor. Okay. And I think it all depends on what else is going on the drawing. So you're going to notice here that they picked these as good and they picked these as poor. Most often you're going to be putting your drawing on a drawing where the orientation of the paper is going to be 8.5 high by 11 long. So in, what do they call that? Landscape mode, if you would. Okay, the long way. And then you're going to have usually a title block down here. Okay. But then you have the rest of the paper. I mean, I'm going to say, I don't necessarily think this is a bad view or this is a bad view. They're both an orthographic projection. I think it just depends on what seems to make the most sense. And if you're going to be adding dimensions, are they all going to fit the way that you have them on here? Okay. I actually prefer the horizontal. I tend to go front view, right side view as just a natural thing that I do if I'm going to use 2 views instead of 3. Okay. But then orientation on the paper is probably going to be the second consideration. So I think you could say these are preferred. This is okay. All right. I don't think these are poor. The next one here, one view. This one, I want to tell you, I don't agree with this slide at all. Look at this drawing for just a little bit. They have one view, okay, one profile view. And remember, I told you want at least 2 views. So first of all, they're violating that. That's a standard, okay? But another reason is because as we look at this, notice that there's a center line going down the middle here, right? And as I told you earlier, a center line signifies the center of a circular feature. Do you see this right here? That's a symbol for a square. If somebody would glance at this and not see a side view where there's literally a square, right? Don't you think they could possibly make this as a circular part on the end there and be a diameter of? Absolutely. So this is a case where side view would be essential, especially when we have a part like this. They might say, oh, but it says the stock is square and I've got the symbol. Did you ever hear that saying about assuming? Yeah. You can't assume somebody's going to catch that. You got to be super clear. Okay. And you might be like, well, it was there. They're going to be like, well, I didn't see it. And now I've got to remake 4,500 parts. I don't know, however many, but right, they're going to be scrapped. They're not going to work. So it's really important that we're very clear and drawing an extra view. I just can't emphasize this enough. Designers, CAD operators, engineers, they draw this drawing once. Take the extra time, 5 minutes, not even, a couple minutes to create that side view, dimension it appropriately. Now you're not going to have misinterpretations down the line that could cost money. Okay. The next one here is choosing the best front view. So when we look at a car, the major shape of the car is usually going to be that side view that we see there, right? Okay. And we want to show it in its natural state. We're not going to show it going up or down a hill. Okay. So show it just horizontal, like normal. And then when we think about a side view, okay, on a car, the front of it, if you would, the right side view here looks very different than the left side. So you would want to include not only a right side, but also a left side because the back side of the car is going to look different. And then you would also want to do a top view. And does the bottom look a lot different than the top? Sure does. It might be a candidate for actually having 1, 2, 3, 4, 5, right? Because there are different elements on each one of those views. So that's how you want to look at everything. Okay. Like, am I getting more and more clear information from adding a view? Like I said, 2 minimum, 3 covers a lot. You might have to add 4s and 5s if you need to. Okay. And then the other orientations here are just, now this would be a poor choice for a front view, but not for a right side view. Okay. Third angle projection. Third angle projection is in the United States and in Canada, nowhere else in the world. You know how the rest of the world got the metric system right? Ours, God darn it, really? 12 inches in a foot, 36 inches in a yard. The metric system is so easy. It's based on tens, right? Like boom, boom, boom. You can, figure out what a millimeter is, how many millimeters are in a meter and all that kind of stuff. It's easy. In the English system, we gotta write it out. We gotta convert it. We gotta get all the numbers. Hopefully I multiplied right or divided wrong, right? Okay. But this we got right, I swear. So third angle projection. Third angle projection is what we've been talking about, where we've got our glass box and whatever we see, we project to that plane that we're looking through. Okay, that's our paper, if you would. Okay. First angle projection, I'm going to go 2 ahead. First angle projection, here's your glass box, and they project to the back side. What? The right side view is going to be actually on the left side of the paper. I know, you're looking at it like, what the heck, right? Doesn't make sense. We got this one right. We totally got this one right. Now, on drawings, you might work with drawings where you are seeing them that were generated in other countries. This is where it's important. You have to be able to recognize the symbol here for first angle projection. So when we look at the symbol, this is a solid conical cylinder, okay? Notice that this circle, this inside circle is on this side. They're projecting in this direction. If we were in third angle projection, that inner circle would be hidden because we'd be looking through material. Do you see that? So our third angle projection symbol has this on the left-hand side. Every one of the title blocks that anyone has, it's standard. They have to show, are they in first angle or third angle? Now, just because something is a metric drawing does not mean it's in first angle projection. Actually, most drawings are in third angle because they're generated here and they're used here. But if you have a company that you're working for and they have a subsidiary or they bought a company in another country and those were engineered and drawn there, there's a good chance they're in first angle projection and it's all backwards. So just something to be aware of. We are not going to be practicing, or I'm not going to have you guys draw in first angle or anything like that. Our standard here in the United States and what we teach in this program and what we have regional here at the companies that you would potentially work for is all third angle projection. Okay. All right. So everything that we've been looking at has been third angle projection the right way. The next one here, laying out this part. So you're going to notice that they use their glass box example. They picked their front view, they have a top view, and then they have a side view. Okay, right side view. I think this is a perfectly good way to lay out this part. Actually, I think it's the preferred way that most people think of front view, and the right side view is off of the front view. Because of the title block down here, they chose to do the side view projecting off the top view. For space-wise, I think it's okay. Interpretation-wise, I don't know if I can care for it. Because remember, in CAD, now, if you're drawing this manually, it's maybe a little bit different, but in CAD, we literally can move these views around. We can scale them very easily to fit on the drawing a little bit better. And I believe that this would be a better way. They call this wasted space. Remember, when we are drawing models, and again, this class isn't just for the AutoCAD we're going to be doing, but when we're drawing models in SolidWorks, which you're going to have next term, we're going to put our orthographically projected or our pictorial view right up here. Will not be wasted space. Okay. So just be aware that a lot of times when we're doing top front, usually it's right side or left side view projected off the front view is the most common and probably the most standard way to do it. So I don't think this is poor at all. Okay. This is valid and this is okay. If they want to say better to use the space that they have there, if they're not going to get a pictorial in there, okay. But this is perfectly acceptable as well. We talked about first angle projection. We're not going to worry about it. We've already looked at hidden lines. Hidden lines are going to be in a view where when we look at that projection, we don't physically see it. So if we look at this part as a front view right here in this direction, we're not going to see that countersunk hole that is interior to the material, but we don't want to forget about it. Okay. As I said earlier, we have to show every one of our features in at least two views. And one of those views might be we see it as a hidden line. It gives us perspective of what it is. In a top view of a countersink, we're just going to see two circles, one, sharing the same center as the other. But in this view, this gives us a better view that, oh, that's a countersunk hole and not a counterbored hole or something like that. Okay. And we'll see those differences as we go along. But always putting all the hidden features in all the views is very important. Okay. And that's something you're going to practice a lot here in AutoCAD. When we create the multi-view drawings, like I said, it's not this week yet. I think it starts next week. Your responsibility is going to be projecting, the hidden views in all of the views. Or the hidden lines in all of the views so that you can, get a more complete picture. So hidden lines are going to be for features that we don't see off of that view. Center lines are going to depict the axes of cylindrical features. Okay. Now, the way that we show center lines, you're going to notice here, when I show it on the right-hand side here, we have our crosshairs in the middle when we see, for instance, a circle as a circular feature. And then we're going to show our long lines on our center lines. And they're going to go just beyond, little bit beyond the actual feature itself that has that as a center point. So notice that these lines go a little bit beyond the circle, okay? They don't stop at the circle. That's a common mistake that people make early on. Do not stop your center lines at the feature. They always extend a little bit beyond. The center lines that we see here that are going through, that are depicting, in this case, the hidden edges of the circle as it goes through that block. You're going to notice that the center line extends a little bit beyond the block on the top and on the bottom. Okay. That's standard. You don't stop it at the block. Okay. Precedence lines. So inevitably, you're going to have lines that are going to line up with one another from view to view. And one is going to be on top of the other. Which one do we show? So the precedence, first of all, is any visible lines get precedence over any other line. So if we see an edge and there's a hidden line in back of it, we only show it as an edge. Okay. So, or And that's what we see here. We see B. So B is right here. If we go left, 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 it would be a hidden line for the top of the hole. We do not show B as a hidden line. We show it only as the closest edge because we're going to see the edge first. Okay, so it is an edge. Then you're going to notice that there is a hidden line. If we go across, 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 there is a hidden line back here for this edge. So we're going to look through material, through the hole, and you're going to notice that there's an edge back here. So we need to show a hidden line. Now, the hidden line takes precedence over the center line. This hidden line is in line with the center line. So if there wasn't this edge back here, we would be showing this as a center line. But because a hidden line has precedence over a center line. So if you would, visible lines are always more important than any other line, okay? Second most important is going to be a hidden line. Third most important is going to be a center line, and that is only when they overlap, okay? Does that make sense? If they don't overlap, then they're just normal, okay? It's only when we have this idea of overlapping. So if we look at the top here, line A is solid here, but you're going to notice that it's going to be in line with the center line. They do show the center line peeking out the end, okay? That's okay, but in part, on the part itself, it's going to be that visible edge, okay, that we're gonna show because it takes precedence over a center line. Center lines, as I said earlier, whenever we show them as part of, we call it a center mark when it's for a circle. We go just beyond when it's a center line. You're going to notice it goes just beyond the actual part itself. So there's not much I want to really say about this, except those are some good examples, okay, of how we show center lines. And whenever they're there, you have to put them in. So if there's any circular features, you're going to be adding them. What is nice is we have an automatic way of doing it. You don't have to manually draw them in AutoCAD. So I'll be showing you that command when we get there. Developing views of a 3D model. I'm going to kind of skip this. This is kind of a nice example of, first of all, this is a sheet metal part. Sometimes if we just have the views here, they're not easy to look at and try to visualize what that part looks like. And that's where that pictorial of whatever the model was that was created, if you've got it, put it in there. It's going to always help people. People who are making the part or who've generated the part or who have a good understanding of blueprint reading, if you would, or print reading, they're not always the only people that are looking at the print. There are people in purchasing that are going to look at the print, and they're going to be responsible for sourcing maybe a part out and buying it from the outside, and they're the point person for getting that done. If they're looking at this and this doesn't have a pictorial view, some people might have difficulties really trying to figure out what the heck is that, right? And visualizing it. So these are nice to have whenever possible. Placing your views. And this is something that's going to come with experience, but keep in mind that you've got a piece of paper. And when we pull in what we call our borders, we're going to pull them in around our views. Over here, you're going to notice you're going to have the views and it says it's too close. Remember, they're not showing them on these, but we've got to get dimensions in there because part of it is not only putting the views in place, but now we're going to be adding the numbers for how big or small those features are and how they're related to one another. So we've got to add some dimensions. So there's too close in this case. Over here, you separate them. Well, now we're too far apart, okay? Because you want to be able to easily see the relationships from one view to another. And over here, I guess this one's just right. Okay, so we can see that we're going to be able to add some things here. And what's kind of funny is look at where they put their right side view. Didn't they say earlier that that was a poor position for a right side view? Yeah, it's not. It's not. It's very common. And as long as you can get your dimensions around and it's not too squished, you're totally fine. We talked about an isometric view. When we've got it, we're gonna add it. So especially in 3D parametrics, because we're literally creating the model and then we add the views. So whenever we have it, always add it as long as there's room. Now this slide here, it says it takes practice to envision what something's going to look like. So as you look here, we've got three views. Here's our front view, top view, and a right side view. And I would just want you to kind of, I know not all of us have a lot of experience with this. So if you can't visualize what this is going to be, it's totally fine. But take just 20 seconds to kind of look at this and be like, huh, these are an orthographic projection. They're lined up, side to side and so on from view to view. We go to page 258 in our textbook. This is the part. Like an isometric. Okay, so 258 in your book. So if we kind of go back and forth here are the three views. Do you see how an isometric becomes super duper helpful, right? And especially for somebody, even if you're versed at it, that's not easy to look at, okay? You got to kind of really study it and figure out which lines are which. So here are the three views again. Sticking that isometric right up here on a drawing becomes really, really nice, okay? All right. Okay. Views of surfaces, normal surfaces, we're going to see those as like their true size and shape. For instance, we're going to see this if we look down at this in a top view as a square and a rectangle, okay? But if we have inclined surfaces, this is where they're going to be foreshortened, okay? So when we look straight down, this point is higher than that point. And so even though we're going to see it as a rectangle, it'll look very similar to this, the length of that surface is not the same. Okay, so we end up having to create extra views in order to show those. And that's gonna be a little bit later in our class. I think that's gonna be maybe probably 2 or 3 weeks down the road where we create what we call auxiliary views. So we can get the true size and shape of that surface, okay? Section views will help us with some of those internals as well. Oblique surface as well. If we need to see, what the true size and shape is of that, if you would, triangle that was caught off of there, we would have to get at it with an auxiliary view to look straight at it. So principal views are only going to take care of like normal surfaces. But then if we have things that are inclined or at obliques, then we're going to have to consider additional views called auxiliary views. Angles, we talked about angles already. Angle is going to be the angle between two lines. So we're going to see that we're going to be dimensioning those types of things and generating them as well. Similar shapes on surfaces. We're going to get some practice with this in our homework. And then interpreting views, okay? One method of interpreting views is to kind of reverse, it says, the mental process. So if we start here and we start to visualize, and this is what you're going to end up starting to do. What's nice about being in mechanical design is that you see it from both perspectives. You see it from the end position, but you also are going to be generating them. So like I said, it's not going to take long and your visualization skills will get actually pretty good. So if you just have these three views here and you try to figure out how something looks, this is how I kind of do it is, okay, you've got your front view. And now what you do is you kind of project the top view and then you kind of go to the right side view and that's where we see our cutout. So I don't know, this is kind of a neat little slide to kind of go backwards in the process. Usually in the examples we had, we were starting here and kind of looking in this direction. But if we start over here, this is the view that a lot of people see at the end result of you laying something out. Now they've got to go backwards and visualize, okay? Isometric, fairly nice, right? If we have it. And we talked about models already. Okay, so that takes us to the end of chapter 6. And now we're ready to start looking at that homework assignment 2A. Okay, so I'm going to stop here and I'll come back and we'll talk about that homework assignment.